to the cloud. So from last time we have seen this. I will go on formulate even more what happened if we have example 1, what happened if we have let fx equals to natural log of x, which means that's equals to natural log of x for x greater than 0 and natural log of negative x for x negative. Then find f inverse x, f prime x. Find f prime x. Solution. For x greater than 0, we have seen that f prime x is equal to 1 over x. We have seen that before, right? Derivative of ln x. Now, but what happens if we have x to be negative? Then the derivative of natural log of negative x, I'm sorry, I should use parentheses here. Respect to x will be 1 over negative x times the derivative of negative x. That is 1 over negative x times negative 1. That's 1 over x. Okay, so in short, basically, so f prime x is equal to 1 over x as long as x is not equal to 0. Okay, in other words, the derivative of natural log of absolute of x respect to x is also 1 over x. Now, we will go backward later on, therefore, the integral of 1 over x dx is natural log of the absolute of x plus constant. Now, those are for the theory. Now, let's go on with the application. Apply this into the derivative and integral of natural log. I do problems from the book. For example, I do question number 6. Or should I start with number 4 now? Yeah. Number 4. We can do a lot of problems today. Number 4. Fx equals to natural log of sine square x. So f prime x will be 1 over blah times the derivative of blah, which will be 1 over sine square x times 2 sine x cosine x. Oh, I can cancel one of the sine, huh? Right? I can cancel one of the sine. So that will be 2 cotangent x. Now, what happens if the base is not e? So suppose, for example, I change that question into gx equals to log of sine squared x. If I don't write the base, then it is base 10, right? Then what I will do first, I do change of base. Natural log of sine squared x over natural log of 10. I do change of base first. Now you will see that if the base is 10, then the derivative will have, if the base is 10, then the derivative will have the change of base first, right? And then 1 over blah times the derivative of blah. Oops, sorry, there should be a prime there. So that's the only extra thing we have here because of that base 10. While this part is basically what we have from derivative of natural log of sine squared. Okay, so if you have a logarithm with base other than e, then you basically have extra change of base material. Okay, so this will be 2 cotangent x over natural log of 10. Is it okay? Let's see more. That's for number 4, implicitly with number 8. How about number 10? Number 10, Fu equals to U over 1 plus ln U. So what is F prime U? I think I will use quotient rule. Right? Quotient rule will have U prime times 1 plus ln U minus U times 1 plus ln U prime. If you can compute this right away, go ahead. So the derivative of U respect to U is 1. So this is 1 plus ln U. Okay. Minus U times derivative of 1 is 0. Derivative of ln U is 1. Oh, I'm sorry. I have squared here at the bottom. So that will be 1 plus ln U minus 1 over 1 plus ln U squared, which will be ln U over 1 plus ln U being squared. Number 12 is actually an interesting question. I think that's actually the derivative is something special. So let me ask you to try it if you don't mind. So hx equals to natural log of x plus square root of x squared minus 1. And what is the h prime of x? As I remember, that's something really nice. You do it, I do it too. You do it, I do it too. So derivative of natural log of blah is 1 over blah times the derivative of blah. I keep the denominator. On the numerator, I will have derivative of x respect to x is 1 derivative of square root is 1 over 2 square root of x squared minus 1 times 2x. I don't like complex fractions. Let me multiply by the LCD. 2 square root of x squared minus 1 over 2 square root of x squared minus 1. Then I will get on the top 2 square root of x squared minus 1 plus 2x. That's what happened on the top. At the bottom, I have 2x square root of x squared minus 1 plus 2 times x squared minus 1. Actually, I can factor the 2 on the top. I know it becomes really something quite nice, so let me try to factor as much as possible. I can take the 2 out. I think I will take the square root of x squared minus 1 out also. So I get x plus square root of 2x squared, square root of x squared minus 1. So you see something cancel there? So I get this is equal to 1 over square root of x squared minus 1. Right? You didn't expect that to be that simple, right? You didn't expect that to be that simple. By the way, this result is quite important. Why? Implicitly, we are saying later on, note, if you can memorize, that would be great, that integral of dx over square root of x squared minus 1 is equal to natural log of x plus square root of x squared minus 1 plus constant. That's what this implicitly means. I happen to see that question, so I work it out. That's for number 12. How about number 16? Y equals to natural log of 1 plus t minus t squared. Ooh, this is hard. Y equals to 1 plus t minus t squared. Any idea? Let's see. Let's find the critical points first, even though I don't think that's necessary. Yeah, this is. I suspect that y prime equals to 1 over this guy times the derivative of this guy. So there will be 1 minus 2t over 1 plus t minus t squared. Okay, but let's see the detail. Let's see the detail. I would like to see the detail. See, the thing is like 1 plus t minus t squared, maybe positive, maybe negative. I don't know. Okay, let's find the critical number first. Okay, so the a is equals to -1, the b is 1, the c is 1. So the discriminant is b squared minus 4ac, that's equals to 5. Okay, so the critical numbers x1, 2 will be negative b plus minus square root of the discriminant over 2. So that's -1 plus minus square root of 5 of 2. Let me split it instead. So the critical numbers are -1 minus square root of 5 over 2. This is where it is located, -1 minus square root of 5 over 2. And x2 is -1 plus square root of 5 over 2. Right? So it is positive in between those, negative otherwise. So we can say that y is equal to 1 plus t minus t squared for x between, I'm sorry, with ln. But the natural log of 1 plus t minus t squared for x between -1 minus radical 5 over 2, -1 plus radical 5 over 2. Then the y prime for that branch will be 1 minus 2t over 1 plus t minus t squared. Okay, for that branch. Now I want to show you that even if it is outside of this interval, we still get the same result for the derivative. Okay, so this is natural log of t squared minus t minus 1. Right? The opposite of that, right? Okay, for I think I can just say otherwise. The derivative of that will be 1 over t squared minus t minus 1 times the derivative of the blah, which is 2t minus 1. But this is actually negative of 1 minus 2t, and at the bottom that's negative of 1 plus t minus t squared. Right, the negative cancel. Right, so y prime will be equals to 1 minus 2t over 1 plus t minus t squared. Okay, as we expect to happen earlier. You see, you can do it short way, okay, but if you want to analyze that further, that's actually the long way to do it. Okay, we still get the same answer though. Okay, now what we did here actually in line to the theory we did a lot earlier. Okay, a lot earlier give us the same result. So, for example, how do we use that for number, for example, number 22? Number 22, y equals to natural log of absolute cosine of natural logarithm of x. So y prime will be 1 over blah times the derivative of the blah. Which will be 1 over blah. The derivative of cosine is negative sine of ln x times the derivative of ln x is 1 over x. That gives us negative tangent of ln x over x. Number 26. Ft equals to 3 to the cosine of 2t. Actually, let me do this problem first, and then I go to other case, a more general situation. Basically, what is the derivative of exponential function whose base is not e? Okay, what is the derivative of exponential function whose base is not e? Okay, so let me rewrite this ft as the following. This is e to the ln 3 to the power of cosine 2t. So this is e to the ln 3 cosine 2t. Therefore, the derivative of e to the blah is itself times derivative of blah. Okay, but this guy here is itself 3 to the cosine 2t. This ln 3 here is just a coefficient, so derivative of that will be just a coefficient of negative sine 2t times 2. So this is negative 2 sine 2t ln 3 to the cosine 2t. Basically, you see that what we have here is that we have some change of base getting involved. We have some change of base getting involved. Let's do the more general case. In general, if I have fx equals to a to the x, which I can write as e to the ln a to the x, which is equal to e to the x ln a. So the derivative will be itself times derivative of x ln a. That is e to the x ln a times ln a. But this is actually a to the x times ln a. Okay, so you see, if the base is not e, then the derivative will be the same thing times the change of base. Now, in more general case, let's say y equals to a to the u. So you will see y prime equals to, the derivative will be itself times the change of base times u prime. Now you will see that's basically what happened in number 26. It will be itself, change of base, derivative of the u. Okay, I hope you see that. Now it will be nice if you can memorize this. Okay? And I believe you can memorize that if you, of course, get used to it. Okay. Number 30 is also an important one. Let me see. Can you also change fx to y and take the ln both sides? That's the logarithmic differentiation. I will show you that later on. But we have not done that, though. We have not done that. We have not done that. In other words, maybe I say it this way. In other words, we can find the derivative of exponential function with base non-e, whose base is not e, okay, without using logarithmic differentiation. That's what I want to emphasize. Okay, so we don't need to use a tool that we learn later to solve the problem we have right now. You can, okay, but it's actually not really ethical for me to use, for example, the material from Calculus 3 to solve problems in Calculus 2, right? If I throw in a question like that, you'll be so pissed off, right? Okay, now likewise here, can we use the tool that we already have right now to do this kind of problem without quoting logarithmic differentiation that we will learn later, okay? Yeah, but I will show you that method later on. Number 30 is another important result. Number 30, y equals to natural log of secant x plus tangent x. Then what is y prime? Y prime of natural log is natural log of blah. The derivative is 1 over blah times derivative of blah. Derivative of secant is what is the derivative of secant? Anybody remember? Secant tangent, good. How about the derivative of tangent? Secant squared. Now, by the way, that's from your Calculus 1 though. That's something you should have learned from your Calculus 1. So whoever your Calculus 1 teacher, okay, you know, if he or she didn't emphasize that you should memorize that, then you better memorize it now, okay? You better memorize it now. If I were your Calc 1 teacher, I would have told you that you need to memorize those. Now, notice that on the numerator, this part here, you have common factor secant x. Okay? If I factor that out, secant x, then I will get tangent x plus secant x whose group cancels the denominator. So the derivative of natural log of secant x plus tangent x is secant x. Okay, now then what is the derivative of secant x? Oh, we did that earlier. That's secant x tangent x. That's Mickey Mouse. Now with this said though, then note, let me write it in blue. Then note, what happened? Implicit later on, integral of secant x dx is equal to natural log of absolute secant x plus tangent x plus constant. Implicitly, that's what we have. Okay, implicitly, that's what we have. Notice that the same rule will apply even if I use absolute sign here. Do you realize that? Right? The same rule will apply if I use absolute sign there. Okay, that's for number 30. Next theory, logarithmic differentiation. Logarithmic differentiation. Let me show you first the benefit, maybe not really the benefit. Like one of the example we have earlier in number 26. Number 26, ft equals to 3 cosine 2t. Okay. Now logarithmic differentiation basically applying natural log to both sides. So let's say this is my y here. Okay, and then I apply natural log to both sides. So I get natural log of y equals to cosine 2t times natural log of 3. Now then, from here we do implicit differentiation. The derivative of natural log of y is 1 over y times y prime. And on the right-hand side, we will have the derivative of cosine 3t is negative 2 sine 2t times natural log of 3. So y prime is negative 2 sine 2t times natural log of 3 times the y, which is 3 to the cosine 2t. So you apply the natural log first, and then do implicit differentiation, and then get the y prime back. Okay? That's the basic idea of logarithmic differentiation. Now, however, this becomes very useful if we are trying to do the derivative of ugly function, looks like number 44. If we have y equals to e to the negative x cosine squared x over x squared plus x plus 1. Now, if you try to do the derivative regular way, then you must have quotient rule and product rule all get together. It's quite messy. It becomes quite messy. So instead of doing so, we apply natural log first. So we proceed with logarithmic differentiation. Now, the nice thing about logarithmic differentiation is it will change the product and quotient into sum and difference. So in other words, natural log of y then becomes natural log of e to the negative x plus natural log of cosine squared x minus natural log of x squared plus x plus 1. Okay, if I simplify a little bit, this is negative x, right? This is plus 2 natural log of cosine x, right? Because the exponent moved to the front. Okay, and the last guy stays the same. When I apply the implicit differentiation, I get 1 over y prime here. This is negative 1. And then minus 2 tangent x. I wonder if you see it. Let me slow down. Negative 2 plus 2 times 1 over cosine x times negative sine x minus 1 over x squared plus x plus 1 times the derivative of blah is 2x plus 1. Okay, so this is now negative 1 minus 2 tangent x minus 2x plus 1 over x squared plus x plus 1. Then the y prime will be, I multiply both sides by y. Okay, let me factor the negative 1. Negative of 1 plus 2 tangent x plus 2x plus of 1 over x squared plus x plus 1 times y. But what is my y again? That ugly guy. E to the negative x cosine squared x over x squared plus x plus 1. Wow, that's so ugly, huh? Now, number 46 can be done similarly. Now, the main purpose of this logarithmic, maybe I write it down. The main purpose of logarithmic differentiation is to differentiate a function fx which is in form of u to the, let's say, w, where u is a function of x and w also a function of x. Okay, now don't memorize this, but the work will be pretty much is done in the following way. So we apply natural log of y equals to natural log of u to the w. So I move the w to the front. Remember that the w and u are both function of x. So when I do implicit differentiation, I get 1 over y times y prime equals to u prime ln u plus w times 1 over u times u prime. And then y prime equals to w prime ln u plus w u prime over u, all of them multiplied by y, which is, now don't try to memorize this, which is u to the w. Don't try to memorize this, it's too long. But it gives you the idea. If you have blah, a function of x to the function of x, and you need to do the derivative, then what will happen? Let's say, for example, I do number 52. Number 52. Y equals to a function of x to the function of x. Now apply natural log first. So natural log of y equals to natural log of x times natural log of sine x. Then implicit differentiation gives me 1 over y prime equals to 1 over x ln sine x plus ln x times, can I go ahead with cotangent x? I hope you don't mind. So y prime therefore equals to ln sine x over x plus ln x cotangent x, all of them multiplied by y, which is sine x to the power of ln x. Okay, that's what implicit differentiation for. Now I see a nice question somewhere here, number 56. They use a red color in my textbook, so let's take a look. Number 56. X to the y equals to y to the x. Find y prime. Yeah, the thing is, x is a function of y is a function of x, basically, right? Okay, so what I think I will do is I apply natural log to both sides, right? Natural log of x to the y equals to natural log of y to the x. That brings us y natural log of x equals to x natural log of y. Now, don't try to solve for y. No. Remember that implicit differentiation is there to help us finding the derivative of that equation without the need of isolating the y first. Okay, so we can just go ahead doing implicit differentiation here. Okay, so this would be y prime natural log of x plus y times 1 over x equals to natural log of y plus x times 1 over y. Oh, times y prime, my bad. Okay. If you want to clean up the denominator, go ahead, multiply by xy, right? But that's just technique. That's quite into technique of simplification. Multiply by xy, so I get x, oops. I get xy ln xy times y prime plus y squared equals to xy ln y plus x squared y prime. I'll put the y prime together. Xy ln x y prime minus x squared y prime equals to xy ln y minus y squared. So this becomes xy ln x minus x squared y prime equals to xy ln y minus y squared. So my y prime will be this ugly thing. I wonder if factoring it will help. No, it doesn't. So xy ln y minus y squared over xy ln x minus x squared. Is it okay? And yeah, because we have an equation which is not necessarily a function. This is an equation which is not necessarily a function. Then our y prime may include y in the y prime. Okay. Furthermore, how about the integral, the antiderivative? Apparently, what we need to remember is integral of 1 over x dx is natural log of x plus constant. That's what you need to remember. So how about, for example, number 74, the easy one, integral from 4 to 9 of square root of x plus 1 over square root of x squared dx. Is antiderivative integral? Yes, that's right. How do we integrate that? This is equal to, I will FOIL it first. Integral from 4 to 9 of x plus 2 plus 1 over x dx. I hope you see how I get that. If not, then do your algebra. Now then the antiderivative will be 1/2 x squared plus 2x plus natural log of absolute x from 4 to 9. And this is equal to 81 over 2 plus 18 plus natural log of 9 minus 8 plus 8 plus natural log of 4. Okay, and from there you can compute yourself. I hope so. Okay, Oh, by the way, when I say to you compute yourself, I do not want you to just plug that into calculator. No, no, no. In fact, I don't like that answer. Okay, I want you to give me the exact solution first. So, and simplify as much as possible. Don't give me decimal. Don't give me decimal. Let me just compute it then. So what's that? 40.5. 40.5, that's 32.5 plus 10, that's 42.5 plus ln9, that's 2 ln3 minus 2 ln2. Okay, then I want you to just leave it like that instead of giving me decimal. What I don't want, the worst one I have was somebody, I wrote this question here. I wrote this is the question, and that person just give me this, like some decimal right away. Okay, no, no, don't do that. I want to see the process. Okay, and I don't really want to get the approximated answer. Okay, I want the exact solution. Okay, I want the exact solution. Why cannot be listed? I want the exact solution. Even if I want the approximated answer, I want you to give me the exact solution first, and then you make it into approximated. If you combine ln9 minus ln4 to ln9 over 4, that's okay also. That's also okay. So you can write it as, you can also write it as 85 over 2 plus ln 9 over 4. That's also okay. Yeah, but don't get to decimal right away. Don't get to the decimal with approximation in which you need to do truncation. No, no. Okay. Every time I ask you to find, even if I ask you to give me the approximate answer, I want you to give me the exact solution first. Okay, I want you to give me the exact solution first. I will give you a break, but together with that break, I would like you to do some problem. I think number 78 is an easy question, should be, if you know what to do. Right? Integral of cosine x over 2 plus sine x dx. And then that should take you like around 2 minutes. And then number 82. Integral of x times 2 to the x squared dx. Okay, so that should take you, this one here, you do substitution first. So you, but the issue it will be, what is the integral of a to the x? What is the integral of a to the x? Now I can give you a hint. The derivative of a to the x, the derivative of a to the x is itself times ln x. I'm sorry, ln a. Okay, that's one big hint. Therefore, integral of a to the x will be itself divided by ln a. I missed the dx, I'm sorry. I keep on missing the dx. Okay, anyway, it will take you 1, 2, 3, 4, 5 plus 10 minutes, 15 minutes. Let's come back at 8:40. Come back at 8, no, 40 is too much. Yeah, that's right, 8:40. Approximately. Okay, so you have 10 minutes break and approximately 10 minutes to do these two problems. Okay, so we come back at 8:40. Here we will do u sub, right? U equals to 2 plus sine x. So the derivative is cosine x dx, which then the integral becomes 1 over u du. This is our du. This is our du. This is our du. Okay, and then the integral of that is natural log of absolute of u plus constant. Don't forget, every time you're done with your integral, indefinite integral, you need to put the plus constant right away. And then I substitute the u back. That's natural log of 2 plus sine x plus u plus c. That's for number 78. And then last one, number 82. Number 82, integral of x times 2 to the x squared dx. Substitution, u equals to x squared, so du equals to 2x dx. Or x dx will be seen as du over 2. My x dx will be this guy. That's our x dx. So the integral now becomes integral of 2 to the u times du over 2. Okay, which is equals to 1/2 times 2 to the u times 1 over ln2, the change of base, right? Don't forget plus constant. Which, if I simplify further, this is 2 to the u minus 1 over ln2 plus constant. Oh, hold on. I'm not done yet. I need to change the u back. So that's equals to 2 to the x squared minus 1 over ln2 plus constant. Okay, so I'm pretty much done with this section. But there are two questions. The last two questions of this section is actually very interesting. Number 93, the last two questions. Number 93. Show that limit of x approaching 0 of natural log of 1 plus x over x is equal to 1. And somebody suddenly say, Thomas, I do L'Hopital rule. We have not learned L'Hopital rule. So we cannot use the proof. And they give us a hint there. Use the definition of derivative. So solution. I say let fx equals to fx equals to ln 1 plus x. So f1 is, I'm sorry, f0 is ln1. which is 0, huh? Okay. Now the thing is then f prime x by definition of derivative is limit x actually no. Maybe hold on. Not yet. I want to do it this way first. Limit x approaching 0 of natural log of 1 plus x over x. This can be written as limit of x approaching 0 of natural log of 1 plus x minus natural log of 1 plus 0 over x minus 0. In the previous example, what happened to 1/2? What happened to 1/2? I think I just throw it away. This guy here. This 1/2 with this becomes this. Okay. Well, anyway, so what happened is by definition, this is actually limit. Let me write it down first. This is actually limit x approaching 0 of fx minus f0 over x minus 0. But that is actually the derivative of the function at 0. Right? Okay, now what is the derivative of the function at 0? That is equals to 1 over 1 plus x when x equals to 0. That's equals to 1. Okay, because the derivative of f prime x, the derivative of fx is 1 over 1 plus x here, right? Okay, so from there we see that we have proven that limit x approaching 0 of natural log of 1 plus x over x is equal to 1. That's for number 93. Now, how about number 94? If you can memorize number 94, that would be the best. It will save you a plenty of hassle in future. Limit x approaching infinity of 1 plus x over n to the n is equal to e to the x for x greater than 0. When will we be able to use L'Hopital rule? When after I teach you. Yeah, after I teach you. After I teach you L'Hopital rule, then you can use L'Hopital rule. Okay? But before I teach you L'Hopital rule, do not use that. When is that? I don't know. I think that's somewhere in the end of chapter 7. So not right now. Not right now. Is chapter 7 on test 1 part of that? Not all. Your test 1 for sure. Your test 1 will not be in including L'Hopital rule. Oh no, L'Hopital rule is actually the end of chapter 6. My bad. Yeah. Your test 1 will include the first couple of sections of chapter 7. So yeah, your test 1 will include L'Hopital rule. But there will be some limit question in which I told you do it without L'Hopital rule. Then you are dead meat. Okay, L'Hopital rule is not the solution for all your problems. Oh. I have seen questions in which when you try to do L'Hopital rule, you will never end. So don't rely on that too much. I mean, yes, you can do that for a lot of cases, but some elegant problem requires you to do it without L'Hopital rule. Okay, number 94. Number 94, solution, or maybe to be more precise, proof. Okay, proof. This question is quite useful in future. That's why it would be nice if you can memorize this property, okay, this equation. But the proof is actually not as simple also. The proof is not as simple also. Let y equals to 1 plus x over n to the n. I will apply, well, we're supposed to find the limit, right? We're supposed to find the limit. But the thing is we have, if n goes to, let's do the scratch work. When n goes to infinity, then x over n will go to 0. Therefore, 1 plus x over n will go to 1. Right? Okay. So does it mean then 1 plus x over n to the n will be 1 to the n? Will that be equals to 1? Now the answer is no, it's not true. That's not true. Okay, because even though this goes to 1 later on, when n is approaching infinity, not infinity yet, this already gets close to infinity, right? In other words, there's a trade-off, like which goes to infinity. Is this go to infinity first, or this one goes to 1 first? Okay, and the thing is, it is not true that any one of them goes to 1 first or n goes to infinity first. No, no. So the way we apply this, we solve this, I will apply natural log. Natural log of 1 plus x over n to the n, which means natural log of y equals to n times natural log of 1 plus x over n. And then, what should I do? The limit as x goes to infinity of ln y is equals to, actually not x to infinity, it's n to infinity, my bad, that's very crucial. That's my mistake. It should be n. N goes to infinity. No wonder I get confused. Okay, n goes to infinity. That would be limit n goes to infinity of n times natural log of 1 plus x over n. Is it okay so far? let me go on further. This is limit of n goes to infinity of natural log of 1 plus x over n over 1 over n. Is it okay so far? Now on the left-hand side, we know that limit of natural log equals to natural log of limit. N goes to infinity of y. Now let's play further. So when n goes to infinity, what will 1 over n be? Going to 0 from the positive side, right? Going to 0 from the positive side. So what will happen to x over n? It will be 0 positive also. Okay. Actually, no, I cannot say 0 positive. That's actually because it depends on the x though. Okay, but it will be 0. It will be 0. It will be 0. Okay, now take a look on how I will play with this. I will, because when n goes to infinity, then 1 over n will go to 0. Okay, if I call that 1 over n as my u, limit u goes to 0 positive, so this will be 1 plus xu over u. Is it okay? Now don't plug in u equals to 0 right away. No, I need to play a little bit. I need to play a little bit. I need to play further. I will multiply the top and the bottom by x. The top and the bottom by x. What is your purpose, Thomas? My purpose is, when I get limit u going to 0 positive of ln, so I get x ln 1 plus xu over xu. But this is actually xu going to 0, right? I mean, what I have here, this is x times, this guy here is x times 1 over u. I mean, x times 1 over n. So if u going to 0 positive, then xu will go to 0. Actually, because they say u is positive, then we can say this is u positive also. This is, notice how I play with my limit. That's why your limit is important. You have to write it down. Let me call that xu, let me call that w now. Limit w bx ln 1 plus w over w. But from number 93, I pull the x up first so that you can see it better. This is x limit w going to 0 positive. But from number 93, limit blah going to 0 of natural log of 1 plus blah over blah is equals to 1. Now, mind you, on the left-hand side, this is natural log of limit x n goes to infinity of y. So, limit n goes to infinity of y is equal to e to the x. Why did you set it equal to x? No, I don't set it to equals to x. I'm saying that from number 93, we know this is equal to 1 times x. That's equals to x. Okay, I didn't set it to x. I'm saying that this is equal to 1 from number 93. Right? Okay. So then we have limit n goes to infinity of, for y will be, I replace that y back. There will be limit n goes to infinity of 1 plus x over n to the n equals to e to the x. Okay. In other words, for us to do this problem without L'Hopital rule, we need number 93 first. Okay, we need number 93 first. Yeah. By the way, Andre Saldana was my pre-calculus student in summer last year. Where did the ln go in the last part? Where did the ln go in the last part? Which ln? The ln here? The ln here? Yeah, so ln blah equals to x. So blah is e to the x. Right? So the ln being undone becomes e to the x on the other side. I remember you, Andre. I remember you. Okay, so yeah, this question is not easy, right? You see this question, the challenge is, can you do that without L'Hopital rule? Can you do that without L'Hopital rule? Okay, with L'Hopital rule, of course, you can do a lot of things, but at the same time, plenty of things happen even before we found L'Hopital rule. Okay, now this property, this equation here is very important and very nice, because you will see some question in future can be done quite easily if you happen to memorize this. For example, what is the limit of n goes to infinity of 1 plus x over n to the, let's say, a n. This is actually limit n goes to infinity of 1 plus x over n to the n to the power of a. Oops. This is this guy to the power of a of limit 1 plus x over n to the n. But this is e to the x to the power of a. This is e to the ax. Right? Instead of doing the what's that, implicit differentiation or logarithm? I mean, what's that again? The L'Hopital rule. Some people have that in mind. You know, no need. You know, once you know that basic form, you can apply this to a lot of other places. Okay, and mind you that when n goes to infinity, what happened with n? When n goes to infinity, that also means 1 over n goes to 0. And 1 over n goes to 0. To be more precise, goes to 0 positive. Okay, that's a property nice to know. Suggested homework. From this 6.3, I'm sorry, 6.4b. Is this 6.4b or 6.4? I think just 6.4, huh? Not 6.4b. Well, I did part of that earlier, so it will be from number 3 to number 57, and then continue on number 71 to number 81. You know what? You can do up to number 85. Why not? You can also try, you should also try number 89. Okay, that's for 6.4. I will skip 6.5. 6.5 is more into, honestly, some mostly precalculus, but then you can apply that to other things also. Oh, speaking about application, you may want to read 6.5 and take a look that it has a lot to do with the epidemic spread. It has a lot to do with epidemic spread. The way it works is actually very close to, I wonder if, which one would that be? It's actually quite close, not exactly the same. It's quite close to Newton's law of cooling. Yeah, it's very close to Newton's law of cooling. Not exactly the same. I should not say it's exactly the same. Okay, now, but I will not do that one. I'm lazy. Too much application. I will go to 6.6 right away. And last time, I already asked you to read about inverse trig function. When will we do homework for credit? You see that in your assignment. I have an assignment. You go to your assignment, then you will see a quiz for homework there. Okay, let me show you first. So you see that you have quiz 1, 2. It will be due on Monday, 7/25. Okay, the way you do quiz 1, 2 will be the same to the way you did quiz 0. Okay, don't forget that one though. Okay, 6.6. Let's review a little bit on inverse trig functions. I go ahead with the exercise, and then I will go back to the lecture part later on. 6.6 inverse trig functions. Let's do some review from our trigonometry and pre-calculus. Let's say, for example, number 2, part A. What is tangent inverse of radical 3? Keep in mind that tangent inverse of x will give you angle between negative pi over 2 to pi over 2. So in the quadrant system, it will be here, continues to here. Now, therefore, I will not call that quadrant 4 to quadrant 1. I call that quadrant -1 and quadrant 1. I call that quadrant -1 and quadrant 1. Okay, so the way we answer this question, tangent what angle equals to radical 3, and that angle is in quadrant -1 or 1. The answer will be pi over 3. Okay, we know that tangent pi over 3 is equals to radical 3. Now, actually, tangent 4 pi over 3 is also radical 3, but 4 pi over 3 is not an element of quadrant -1 nor quadrant 1. That's why we don't use that one. Okay, and don't forget, inverse function should have a unique solution. It's an inverse function. Part B, how about secant inverse of 2? Let me call this theta. So secant 2 is equal to secant theta, right? Okay, so 1/2 equals to cosine theta. I do the reciprocal. So cosine inverse of 1/2 equals to theta. What will that be? Pi over 3 again. Now, let's see what happened if the value is actually negative. Tangent inverse of negative radical 3. Now, because sine and tangent are odd functions, then sine inverse, cosine inverse also odd functions. Therefore, tangent inverse of negative is equal to negative of tangent inverse. That will be negative pi over 3. Notice that it is in quadrant -1. Okay, in general, tangent inverse of negative x is equals to negative tangent inverse of x. Again, because tangent is an odd function, tangent inverse will also an odd function. Okay. However, it doesn't work for cosine. Cosine inverse of -1/2 should be in quadrant 2. Maybe I write it this way first before I go there. That's why I asked you to review your trigonometry, right? Cosine inverse of x will be in between 0 to pi. Okay, why? Because cosine function is not one-to-one, and they restrict that to quadrant 1 and quadrant 2 to keep it one-to-one. Okay, to make it one-to-one. So cosine inverse of x, therefore, will give us quadrant 1 or quadrant 2. Cosine inverse of a positive number will be quadrant 1. Cosine inverse of negative number will be quadrant 2. And they have this relationship. Cosine inverse of -x is equal to pi minus cosine inverse of x. Let's explain it further. Let me explain it further. Now, the starting point is we know that the answer will be in quadrant 1 and quadrant 2, right? Okay, now suppose this is theta. Okay, then, and this is unit factor, unit circle. So the coordinate here will be cosine theta, sine theta. Right? Now notice what happened if I reflect that with respect to the y-axis. So the coordinate here is cosine negative theta, sine, I'm sorry, cosine, no, negative cosine theta. This is negative cosine theta, sine theta. Right? If this is theta here. Okay, but at the same time, we know that this is equal to pi minus theta. So think about this, that negative cosine theta is equals to cosine of theta minus, pi minus theta. So if cosine theta equals to x, if cosine theta equals to x, then negative x equals to cosine of theta minus pi minus theta. So cosine inverse of negative x equals to pi minus theta. But theta is cosine inverse of x. I basically try to derive what happens if you have cosine inverse of negative number. Let's try further, number 4. Part A, how about cotangent inverse of negative radical 3? If I call this theta, then negative radical 3 equals to cotangent theta. The reciprocal will give me the tangent. So tangent inverse of negative 1 over radical 3. I hope you will later on will see that you can skip from here to here directly by doing the reciprocal. Okay? So theta will be tangent inverse of that will be negative of some angle. That's negative of pi over 6. Part B, what is arc sine of 1? Arc sine of 1, that's sine inverse of 1. What's that? Sine what equals to 1? Over 2. Right? The quiz is homework. Yes, that's the graded homework. When I give you suggested homework, you don't need to turn it in. That's just for you to practice. That's what suggested homework is. Okay? Now, notice that when I give you a quiz, I don't give you in-class quiz, right? So implicitly, that's a take-home quiz. You see what I mean? Yeah. Okay? So you still do it at home. That's what homework is. That's what homework is. You still do it at home. I mean, you are right now at home anyway, supposedly. Right? So should I call you currently working at home by attending my lecture? That's for number 4. The next couple parts is actually quite interesting. For example, number 8. Number 8. Notice that this technique is the technique I show even in my trigonometry and precalculus class. Cosecant of arc cosine of 3 over 5 equals to what? Now, the way I solve that, I will first call this guy my angle theta. Let arc cosine of 3/5 equals to angle theta, which means 3/5 is equals to cosine theta. Now, what's the purpose of me doing that? I want to draw the triangle. These were my theta and right angle here. And cosine of that theta is 3/5. So this is 3, this is 5. By Pythagorean theorem, this is 4. Okay, now notice that this is your theta. So what you need to look for, what you need to do is actually cosecant of theta. So cosecant theta is equals to 5 over 4, right? Reciprocal sum. Therefore, cosecant of arc cosine of 3/5 equals to 5 over 4. How about number 10? Another interesting problem. How about cosine of tangent inverse 2 plus tangent inverse 3? I asked this question in my trigonometry class. And of course, if they knew it, they will be so pissed off with me because I asked questions from Calculus 2 in trigonometry class, while actually this question comes from trigonometry class that you're supposed to know before you come to Calculus 2. Now, how do we solve this? I let theta equals to tangent inverse. Oh, let me call that A instead. So I don't use angle theta, I call that A. And B equals to tangent inverse 3. So tangent A is 2, tangent B is 3. Now from there we draw the triangle. If this is A and right angle here, then this is 2 over 1. If this is B and this is right angle here, this is 3 over 1. The hypotenuse will be square root of 5 here, square root of Okay, now let's go on. So what we need to answer is actually what is cosine A plus B, right? This is my A. This is my B. Then, do you remember what is cosine of sum? Long time no see. Cosine A, cosine B, minus sine A, sine B. Then you look at those triangles. What's cosine A? 1 over radical 5. What's cosine B? 1 over radical 10. Minus what is sine A? 2 over square root of 5. What is sine B? That's 3 over square root of 10. Uh-oh, yeah, you need to memorize those trigonometric formulas, okay? I'm sorry, I wish I have another way, but no, there's no other way. Okay, so this will be 1 minus 6 over square root of 50. That's negative 5 over 5 square root of 2. That's negative 1/2. Okay, that's negative 1/2. Can you tell which quadrant is this cosine, which quadrant is this A plus B located? You know that cosine of the sum is negative 1/2. But how do we then use that to know which quadrant it is located? I call that a follow-up question. You think about it. Which quadrant does tangent inverse 2 plus tangent inverse 3 located? I think I should say is, not does. And more importantly, why? So don't just tell me the answer, but also tell me why. Why quadrant 2? Yes, the answer is quadrant 2. The 2 is square. Now the thing is, you need to combine two things. You say, one of you say that because cosine is negative, cosine of tangent inverse 2 plus tangent inverse 3 is negative. Does it imply, if cosine is negative, does it imply that the angle is in quadrant 2? The answer is no. We only know it is in quadrant 2 or quadrant 3. Maybe in quadrant 2, maybe in quadrant 3. Another reason. Okay, another reason. Now, because 2 is positive, then tangent inverse 2 must be in quadrant 1. Right? In other words, A must be between 0 degree to 90 degrees. Right? It's in quadrant 1, right? Likewise, B is also in quadrant 1. So angle B is between 0 to 90. So A plus B will be between 0 to 180 degrees. So A plus B will be in quadrant 1 or quadrant 2. So from the cosine point of view, it is in quadrant 2 or 3. From inverse tangent point of view, the sum must be in quadrant 1 or quadrant 2. Okay, so A plus B has to be in quadrant 2 or 3 and quadrant 1 or 2. Then for sure it must be in quadrant 3 or quadrant 2. Okay, that's how we argue for that. How about number 14? You try this one. You try this one. Number 14. Number 14. Simplify the expression cosine of 2 times tangent inverse x. My hint is simplify. My hint for you is we start with let A equals to tangent inverse x. Okay, so what do you need to compute later on is cosine of 2A. That's what you need to compute. Okay, let me give you maybe 2 minutes to work this out. Okay, so we let A equals to tangent inverse x, so tangent A equals to x. I draw the triangle. If this is a right angle, this is x, this is 1. This will be square root of 1 plus x squared, right? Now then, cosine 2A is, which formula do you want to use? Either one of them. 2 cosine squared A minus 1, right? That's one of them. Can I use that one? So this is 2 times cosine A, 2x over square root of 1 plus x squared being squared minus 1. That's 2 times x squared over 1 plus x squared minus 1. Fast forward. That's x squared minus 1 over 1 plus x squared. Do you get the same thing, by the way? Anybody get the same thing? Please. Uh-oh. Now, if you don't get the same thing, then you know what? Let me check, just in case I make a mistake. Just in case I make a mistake. Oh, somebody get that? Good. Let me show. That's 2x squared minus the LCD. So I get x squared minus 1 over 1 plus x squared, right? which is the same to that one. Somebody did the notation here. Do you see this? Who did this? Come on, erase it. I don't want to be there. See, because I didn't notate it, then I cannot erase it. Well, anyway, that's the foundation, the algebraic foundation from your trigonometry. Now, I will derive formulas. And we will use this formula on Monday. Derivatives of inverse functions. The first one is sine inverse. Let y equals to sine inverse of x. Let y equals to sine inverse of x. So sine y equals to x. Now we do implicit differentiation. So we do a lot of implicit differentiation today. Implicit differentiation, cosine y times y prime equals to 1. Y prime equals to 1 over cosine y. So y prime equals to 1 over, we have issue here. Cosine y will be plus minus square root of, plus minus square root of, 1 minus sine squared y. That's the square root of 1 minus, what is sine squared y? X. But the problem is, how do I explain the plus minus to disappear? How do I explain that the plus minus disappear? How to eliminate, to be more precise. How to eliminate to get from plus minus square root of 1 minus sine y squared to square root of y minus x squared only. It's more about the plus minus. Well, sine y equals to x. So that one is easy to substitute, right? This guy equals to that guy. Now, my problem is, how about the plus minus? Why suddenly I don't have the plus minus? Any idea? The quadrant restriction, that's right, the quadrant restriction. What happened is this. What happened is sine inverse x will be either in quadrant -1 or quadrant 1, right? Okay, let's call that theta. Let's call that theta, or actually y, to be more precise. That's y. Okay, so what is cosine y? Cosine y will be positive in quadrant 1 and also in quadrant -1, in quadrant 4. Right? Okay, that's why we don't need that plus minus anymore. Okay, that's why we don't need that plus minus anymore. That's why we can just say that cosine y is square root of 1 minus sine squared y, okay, which is plus minus, I'm sorry, which is square root of 1 minus x squared. Okay, that's the reasoning. Second part. How about the derivative of tangent? Let y equals to tangent inverse x. So tangent y equals to x. By implicit differentiation, derivative of tangent is secant squared y times y prime equals to 1. So y prime equals to 1 over secant squared y. But secant squared y equals to 1 over, I'm sorry, secant squared y is 1 plus tangent squared y. Okay, so the derivative of tangent inverse x respect to x is 1 over 1 plus x squared. The derivative of sine inverse x respect to x is 1 over square root of 1 minus x squared. The last one, the derivative of secant inverse x respect to x equals to what? That's our point number 3. Let y equals to secant inverse x. So secant y equals to x. Implicit differentiation. Derivative of secant is secant y tangent y prime equals to 1. So y prime equals to 1 over secant y tangent y. So y prime is equal to 1 over secant y is x, that one is easy. But how about the tangent y? Y equals to secant inverse x. This should be in quadrant 1 and 2, 1 or 2. I think they define it differently though. I'm sorry, our textbook actually define it differently. They make it quadrant 1 and quadrant 3. Our textbook make it in quadrant 1 and quadrant 3. You can see that from page 457. Page 457. That's actually the key. So the other textbook, when they use quadrant 1 and quadrant 2, the result will be with absolute value. Okay, so secant y, which is equals to x, implies tangent y, like that. So because of that, then tangent y is in quadrant 1 or quadrant 3, tangent y will be positive. Right? Okay. But at the same time, tangent y, tangent squared y plus 1 equals to secant squared y. So tangent y will be the positive square root of secant squared y minus 1, which is x squared minus 1. Okay, now I need you to memorize 3 of these such that on Monday when we come back, we can focus on the derivative and integral. And then on Monday also, I will go on to 6.8. So suggested homework from here, 6.6a will be number 1 to number 21. Do I want to do it that way? No, number 1 to number 13 is good enough. And try to think about number 19 and number 21. Okay, when we come back, we will work on number 23 and on. Okay, that's for today.